Joint probabilities and correlation. Session prerequisites. Browse to our earlier material on probability. This is archived under IIMQM101.1X. You must be enrolled into the course to view archived content. In preparation, please have the spreadsheet open on your computer and follow along. Maximum benefit guaranteed. Learning objectives. Build analogs of concepts that we discussed in QM101.1X, like joint, marginal, and conditional probabilities. Highlight a key measure to quantify dependencies called correlation.
We are left with one more question. Given that software X has moved up, what's the likelihood that software Y has also moved up? We've already covered conditional probabilities, so this one's easy. We even use the same notation. Our events are described by variables taking specific values. What we need can be written as probability of y equal to 1 given x is equal to 1. This translates to p y equal to 1 intersection x equal to 1 divided by p x equal to 1. The numerator is a joint probability and the denominator is a marginal probability. Looking up our table, this column denotes x is equal to 1 and this row denotes y is equal to 1. So I just need to focus on this probability as a proportion of this probability, and that is nearly 75%. Knowing that software X has moved up over a month, you can be 75% sure that software Y will follow suit.
I can bet it's vice versa too?
No, Lisa, you must be careful. This is a classic mistake. You must separately calculate probability of x equal to 1 given y is equal to 1. I leave it to you to figure out the answer to that question. There are occasions when knowing the movement of one stock has little effect on the other. Suppose we have a hypothetical stock Z whose monthly movements are recorded by the variable Z. Look up the contingency table of Y versus Z. This we do with a pivot table. I have the values of Y over here and the values of Z column wise. I will drag this once again and only look at the counts. Look up the contingency table of Y versus Z. We have the prior probability P of Z equal to 1 as 121 over 239, which is about 50.6%. We have P of Z equal to 1 given Y equal to 1 as 67 over 132, which is about 50.7%. Not too far away, and that's the posterior probability if you recall. This means knowing that y equal to 1 has had no effect on the probability of z being 1.
Does this mean y and z are mutually exclusive?
Another classic mistake. Most people think this way. Notice that y and z can both be 1.
Oh yes, and that's nearly 28% of the time. Oops.
We say that random variables z and y are independent if the conditional probability is the same as the unconditional probability for all valid values of y. Here's an equivalent definition. Starting with the contingency table, we can build a conditional distribution for z given y. We fix a value of y and look along the row, and then we get our conditional probabilities. Our first entry here is equal to 53 divided by 107, which we fix via the column. I just drag this across and then I bring it down. Notice the fairly similar patterns of entries across all the rows, which is a clear-cut sign of independence.
I like it. Skip worrying about y, just check the margin.
Independence is a rare phenomenon in real life unless it is orchestrated. For instance, successive rolls of a fair die or coin tosses are independent. In a typical case, two variables such as our software stock movements are dependent on each other. From now on, we'll have X and Y stand for the actual movements in the two stocks, not the directions. One measure to quantify their dependence is called covariance. It's written as cov xy and is the expected value of the product of their deviations. The idea of covariance is best explained with a picture. The quadrants here are based on a new set of axes given by the two averages. The green points are where x minus mu x times y minus mu y evaluates to a positive number. The oranges are where the deviations are out of sync with each other. The product becomes negative.
I got that.
Here's the basic idea. If the greens outdo the oranges, then the covariance, which is the average product of the deviations, is generally positive.
Looks like it is, in our case.
Correct. And there's even a spreadsheet function for this, covariance.p for population, which gives us 1666.6.
That's awesome.
Right, and it's not very meaningful too. If we change the units of currency, we'd get a whole new value. We've created an exercise around this. What we will do is to standardize the deviation terms. We'll elaborate on this when we get to normal variables. For now, let's talk about a unitless measure called correlation. It's defined as the covariance of x, y divided by the product of their standard deviations. No matter what the variables are, this measure always lies between -1 and 1 and is a good indicator of how the variables are associated. In our spreadsheet, we now have x replacing movement x and y replacing movement y. So I have correlation given by equal to correl of C colon C and H colon H, which is about 0.58. This number reflects a strong relationship between the two monthly stock movements. Again, we resort to pictures to get an idea of how data points tend to spread out when the correlation between two variables become weak. Notice what happens when the sign changes to negative. In this segment, we have discussed several distributions involving two random variables. All of these constructs can be applied to analyzing business data, as we have amply demonstrated. A correlation of 0 does not always mean that the points look like a swarm of bees. I leave you with an interesting exercise.
Exercise? These bees don't even let me sleep.
Goodbye.